Okay. So here as part of your RC4, we are going to be discussing. So this RC4, the first function and is going to be the initialization of your S. Before we go and do any kind of key generation algorithm and all, so we need to do what? Initialization of the state vector needs to be done in your RC4. Okay. So this RC4 initialization, so first is going to be the S initialization, that is going to be 0 to 255. So S naught is equal to 0, S1 is equal to 1, S2 is equal to 2, like that S255 is equal to 255. Okay. So next one is going to be the temporary vector T. Okay. So this temporary vector T, we are going to be generating this temporary vector from whatever the key is going to be given. So based on that key, we are going to be generating the temporary vector. Okay. So how that is going to be, so I will discuss in the next slides. Okay. So the next key length is going to be of 256 bytes. Okay. So whatever this k is going to be there, so that is going to be transferred to your temporary vector. Already I have said no. So whatever the key is going to be there, that is going to be included as part of your temporary vector, and we are going to be generating a temporary vector. How that is going to be done, I will discuss. Okay. So whatever this key length is going to be there, so that is going to be called as your key length. Okay. So key length bytes. Okay. So KEYLEN bytes you are going to be having. So for first key length elements of your T, so whatever this suppose the key length is going to be of 4 bytes. Okay. S array is going to be of 8 bytes. Okay. So don't think of 255 and all. Okay, so this is going to be converted again into the byte format and all. So these are going to be the bits, right? So it is going to be converted. Right. So now key is going to be of 4 bytes. Okay. So now temporary vector is going to be of whatever this area is going to be there. So until this S of your 256 is going to 256 divided by 8. 128 divided by 8, 16 అంటే 32 bytes వస్తుంది. So 32 bytes means 32 bytes divided by um, so 32 bytes. So the temporary vector should also consist of 32 bytes. With whatever the length of your state vector is going to be there, this temporary vector also should reach that particular same length you are going to be reaching. Okay. So how do you compensate that? Whatever the key is going to be there, suppose key is going to be of 4 bytes. Okay, 4 bytes, 4 bytes, 4 bytes, 4 bytes. So totally you are going to be including the matching the length of your whatever the state vector is going to be there with the temporary vector. How you are going to be matching whatever the key is going to be, that key repetition you are going to be filling the elements of your temporary vector. Okay, so that is going to be a this one. Okay, so as part of initialization and also for I is equal to 0 to 255, if it is going to be of 8 bits, so then it is going to be 0 to 7. If it is going to be of 4 bytes, then it is going to be 0 3. Okay, so here the S of I is equal to I. So for I is equal to 0, it's going to be S of 0 is equal to 0, S of 1 is equal to 1, S of 2 is equal to 2, S of 255 is equal to 255. That's what I have said to you, right? So next temporary vector T of I. So T of I is equal to K of I mod key length. Okay, so this key length is going to be whatever that mod operation of your length is going to be there. So the same value is going to be got as part of this. Okay, suppose key length is going to be 4. I is equal to 0. 0 mod 4 is equal to 4 only. Okay, so K of 4, whatever is going to be there. So those 4 elements are going to be filled into your temporary vector. Okay, if you observe here in this figure, so okay, if you observe in this figure, so S0, 1, 2, 3, 4. So then key length is going to be there. So here, whatever the key is going to be there, that is going to be copied. Again, recopy. Okay, so the next elements and all, so it is going to be recopy. Okay, so the next element, these 4 bits only are going to be 1, 2, 3, 4. Suppose so 1, 2, 3, 4, again 1, 2, 3, 4, again 1, 2, 3, 4 until this length and this length are going to be matching. So this is going to be what as part of your initialization of your state vector. Okay, so S is going to be of 255 bytes. So that's temporary array also should be of 255 bytes. So this is the diagram which is going to be depicting that particular scenario. Okay. Okay, so next we are going to be having the RC4 algorithms and all. So in this RC4 algorithm, what is the main first functionality is going to be nothing but the key scheduling we are going to be doing. So this key scheduling is also going to be called as initial permutation. Okay, so what we are going to be doing, so we are going to be iterating the I is equal to 0 to 255. So if it is going to be of 7 bits, so then it is going to be 8 bits, 8 bytes, then it is going to be 0 to 7. If it is going to be of 4 bytes, so then it is going to be 0 to 3. Okay, so like that you are going to be iterating the I value with a for loop. So whatever this j is going to be, so j is going to be initially taken as 0, 0 plus s of I. Okay, I value is going to be 0. So S of 0 plus T of I. So T of I is nothing but I value is going to be in the first iteration. I value is going to be 0. So it is going to be S0 and T0. Okay. So whatever this value is going to be there. So S of 0 is going to be 0. Already the same thing we have explained in the previous slide. Okay. So then T of 0 is going to be getting the whatever the K value is going to be that value. Okay. So this total value, suppose it is going to be some 3. So 3 mod 256 is going to be 3 only. Okay. So here what is going to happen? So J is equal to 3 if you get. Okay. So swap S of I value in the first iteration is going to be 0. Okay. So next the J value is going to be 3 because we have computed with the mod functionality and we have got it. Suppose here it is going to be only 7 bits or 8 bytes only. Then it is going to be mod 8. If it is going to be of 4 bytes, then it is going to be mod 4. Okay. So like this, whatever the values are going to be there in the state vector at here, S of 0 and S of 3. So those both are going to be swapped with each other and you are going to be getting a same algorithm, your same length of your state array you are going to be having. Only that your S0 and your S3 positions are going to be changed. Values are going to be changed at that particular position respectively. Okay. So that's what is going to happen as part of this function also.
Ma'am, you are in mute, ma'am.
హలో అలేఖ్య
Yeah, ma'am, we can hear you, ma'am.
ఎప్పటి నుంచి మ్యూట్ లో ఉన్నా?
ఒక 1 minute అవుతుంది మ్యామ్ మ్యూట్ లో
1
ఉండి.
మినిటా? ఓకే. థ్యాంక్ యూ. నేను ఇది మూవ్ చేసినప్పుడు అట్లాగా అయినట్టు. థ్యాంక్ యూ.
ఆ,
ఇమ్మీడియట్ గా చెప్పండి అమ్మా, నాకేదైనా ప్రాబ్లం.
ఓకే ఓకే
Okay,
ఓకే.
so this is going to be the initial permutation or the key scheduling algorithm steps. Okay, so as part of your RC4, 3 steps are going to be there. The first step is going to be the key scheduling, or it is also going to be called as the initial permutation. Okay, so this is going to be the S vector array. Okay, so this how you are going to be representing already in your previous slides. I have said that. So it's going to be S naught is equal to I. Whatever that I value is going to be, that is going to be got into your S naught. Okay, so S of I is equal to I. Okay, I value is going to be 0, then S naught is equal to 0. Okay, so if I is equal to 1, S of 1 is equal to I value only, so that is going to be 1. So like that, S naught is equal to 0, S1 is equal to 1, S2 is equal to 2, S3 is equal to 3, S4 is equal to 4, S5 is equal to 5, S6 is equal to 6, S7 is equal to 7. Okay, so this is the how you got these values. Okay, so next you are going to be having key array and your plain text. These both are going to be given by already in your problem, key array and your plain text. Okay, don't worry about it. But you need to generate your S array, you need to generate your T array. Okay, so how the T array is going to be generated? So 1, 2, 3, 6. Okay, whatever the key array elements are going to be there, those are going to be written into your temporary array, and you are going to be matching the length of your S array, and you are going to be getting the temporary array. Okay, so 1 2 3 6 are going to be repeated. Okay, again repeat the 1 2 3 6, because here you are going to be having 8 bytes and the key is going to be of 4 bytes on. So double time 4 bytes is going to be 8 bytes. Okay, so here coming to the key scheduling algorithm, so how many iterations you need to take? So it is going to be depending totally on the size of your S array. Here the size of S array is going to be 8 bytes. Okay, so that 8 bytes you are going to be taking. So I is equal to 0 to 7. So 7. So you are going to have 8 iterations you are going to have. So here, for example, I have placed here the first iteration and the second iteration. So first iteration you are going to have j is equal to 0, because as in the algorithm it is going to be j is equal to 0. Second, your iteration, so I value is going to be 0 to 7, right? So 0 to 7. Okay, so for your 0 to 7, here what is going to be your j value? J value is going to be 0. Here behind the arrow it is going to be 0. 0 plus, again what is the next one? S of I. Okay, I value is going to be 0. So S of 0 is equal to 0. Okay, so 0 is going to be placed here. Okay, plus again what is the T of I value? So I value is going to be 0, temporary vector of 0. Okay, so T of 0 is going to be nothing but here 1. Okay, 0 plus 0 plus 1. So that is going to be 1 mod 8. So any low number, less number with mod greater number. So it's going to be the same number you are going to be getting, because it's going to be taking the remainder. Okay, so 1 mod 8 is going to be 1. So j is equal to 1 now. Okay, so j value is going to be 1 now. Okay, so second iteration your j value is going to be 1. Okay, so here what you need to do after finding the j value, you need to swap S0 and S1. Why S1? Because j value is 1. Here we asked to swap S of I and here S of j. Okay, swap I value is going to be in the first iteration 0, j value which we have computed and we have got it as 1. So swap S0 and S1. Okay, so that's going to be the swapping operation which is going to be done. So finally, whatever the 0 and 1 are going to be there, they both are going to be swapped with each other. And finally, you're going to be getting after first iteration, S value is equal to 1, 0. Here 0, 1 because we have swapped after first iteration. Like that, you need to swap based on your J value. You need to swap I value and J value. You need to swap all these elements. Okay. So like that, how many iterations you need to carry out? 8 iterations. So how you are going to be getting? So number of iterations is equal to size of your S array. Okay. Any doubts? It's not going. Okay, so the second step is going to be the key stream generation. Okay, so what is going to be done in your key stream generation? So like your first key scheduling also, you are going to be doing here certain values are going to be exchanged and all. So how the swapping and all you are going to be doing based on your XOR operation you are going to be doing. Okay, so how it is going to be done, let us see now. Okay, so here what is going to happen? So whatever this value of your k is going to be there and all, so that is going to be XORed. The key value is going to be XORed with the plain text. So that also next byte of the plain text you are going to be XORing. Okay, so that is going for be done for the encryption. Okay, decryption, it is going to be XOR of your key value with the next byte of the cipher text. Okay, so that is going to be for the decryption. So decryption, always the input is going to be your key value and the cipher text. Encryption, always the input is going to be the key value and the plain text. Okay, so this is going to be the stream generation algorithm. So these algorithms are already proposed as part of your RC4. So we are not going to change or propose anything. There is nothing done. So these steps you need to remember as it is. Okay, so here I and j is equal to 0. Okay, while true. Okay, so next what is going to happen? Your I is equal to I plus 1. So what is the I value? 0. Okay, so 0 plus 1. Okay, so that is going to be 1 more 256. 1 more 256 is going to give you a value of 1. Okay, so next j value, I value after first loop, so it is going to be 1. Okay, so the next one is going to be a j. So j is going to be 0. 0 plus s of I value is going to be 0, s of 0. Okay, so next mod 256. Okay, so that is going to be your j 0 plus here s of 0 is equal to 1. So 0 plus 0 is going to be 0 mod 256. So then you are going to be swapping s of I and your s of j. S of I is going to be your here it is going to be did not give there is a post or prefix. Okay. So it's going to be here 0 and here 1 and here 0. Okay, so that's going to be swapped and all. So like that, you're going to be finding the t value and the k value is going to be updated and all. So by this, what will happen? You're going to be getting a new key value. You're going to be getting and all. Look at the slide. So this is how it is going to be got and also whatever the key values are going to be there. So here the number of iterations in your stream generation is equal to size of your key. As part of your key scheduling, number of iterations is equal to size of S array. Okay. So here there is going to be size of your key. Okay. So here what you will be doing and also we are going to have so key 4 అంటే కనుక k0, k1, k2, k3. Okay, so 4 elements you are going to be having. Okay, so this is bytes. Okay, I will correct it later. Okay, so similarly for your S also, previously we have done the 8 iterations, and also based on these operations you are just going to gather your you are going to be getting K0, K1, K2, K3 you are going to be getting. So those are going to be considered as a new key value and all. So those key values only you are going to be considering, and also by this you are also going to be
Ma'am, you are in mute again.
I'm moving your attendance this window. So then it is going to get okay. So the next is going to be a encryption and decryption. So third step which is going to be done in your RC4 is going to be a encryption and decryption. As part of this only, plain text is going to be XORed with your new key value. So first what you are going to be doing, whatever the plain text is going to be got, so that is going to be converted into the binary format. So plain text is going to be given as 1222 as part of your example. Okay, so this is going to be converted into the binary format. So this is going to be a plain text. Okay, key value is also given, right? So that is also 1236 in the, okay, so that is also again converted into the binary format. Okay, so once converted, you are going to be doing the XOR operations and you are going to be obtaining what the ciphertext is going to be got. Okay, so that's how these RC4 is going to be working and all. So this PPT was already shared with you. This multiple encryption and all, I will say in evening class. Okay, so the next one is going to be a block cipher modes of operation. Okay, so these are going to be from your block cipher operations. So this is going to be the third part of your second unit. So where you are going to be having the multiple encryption and your triple DS, and you are also going to be having block cipher operations. So those are going to be your ECB, CBC, and your CFB modes you are going to be having. So these three things I will be covering now. Okay. Okay. So why we require your modes of operation, and also so we are going to be having block ciphers, stream ciphers, many algorithms we are going to be having under your substitution, transposition and all. So then again, why we are going to be going for your modes of operation and all. So these whatever the ciphers we have learned till now, so that is going to be for your ciphertexts are going whatever the things you have done till now, so that is going to be for your short messages. Okay, once you want to do need for your whatever the lengthy messages you want to decrypt them, encrypt them or the decrypt them, so then we require your these modes of operations. And also suppose you want to encrypt and decrypt a lengthy message or a image file or a video file or a voice file, like that, some real application data related things and all you want to send and all. So on online transactions if we are doing and all, suppose you are going to be writing the WhatsApp messages and all, it's going to say that it is going to be encrypted format and end-to-end encryption is going to be allowed. So like that kind of messages and all, we require these modes of operations and all. Okay. Okay, so as part of it, we will learn. So before that, mm, Okay, so this is going to be for your block cipher and all. Okay, so what is going to be done here as part of your block cipher? So block cipher is nothing but whatever the plain text we are going to be converted, that plain text is going to be divided into blocks, and that each block is going to be converted into the ciphertext format. Okay, so here the block cipher is all going to be always a fixed size. Okay, so you are going to be having, suppose n bits of your input, you are going to be getting n bits of output. Suppose you are going to be having some 300 bytes or 300 bits of plain text is going to be there, then 300 bits of cipher text only you need to obtain. Okay, so here as part of your plain text is going to be, it's going to be encrypted with respect to your B bits. How it is going to be done? So you're going to be checking whether the plain text to be encrypted and all is going to be greater than B bits. Okay. So if it is going to be greater than B bits and all, what you need to do, you need to replace with respect to the filling characters and also as part of your block ciphers, you are going to be filling it with the 0 because it's going to be because it is going to be converted. So mostly for the encryptions and also they are going to be converting in the byte form, binary format and all. So it's going to be there. Okay, so here plain text is going to be converted. Okay, so for this, what this NIST people have done, so they have proposed 5 modes of operation, which is going to be defined by NIST. Okay, so here the security, whatever the issues are going to be there and also when multiple blocks are getting encrypted and all. So they are going to be working as part of your block cipher and all. So you are going to have different applications with respect to the different modes of operation you are going to be having. So based on what kind of real-time application you are going to be using. So based on that only you are going to be having the plain text. Okay, so what are the different modes? So we are going to be having 5 modes of your play operation. So the first one is going to be the electronic code book. The next one is going to be your cipher blockchaining. The next one is going to be your cipher feedback, CFB, and the output feedback and a counter. So output feedback and the counter are not required for us to study because they are not part of your syllabus. So once you study these 3 things, so that will be enough. Electronic code book and your cipher block chaining. Okay, cipher feedback. Okay, so these 3 are going to be enough. Okay, first, and one more important point is with respect to your electronic code book and cipher block and your cipher feedback and also they are going to be asking differences and all. So mostly they are going to be bothered about ECB and your CBC. So this is going to be also one short answer questions which you might be getting in your externals. Okay, so compared to your previous external papers, I said that. Okay, so this so electronic code book is going to be a first one. Okay. So what is going to happen? So in your electronic code book or any kind of algorithm as part of your cryptography, what is the input you are going to be taking? So that is nothing but the original message. That original message is nothing but the plain text, right? What is the original message? That is nothing but your plain text. Okay. So this as part of your plain text, whatever this it's going to be a block. So that is going to be nothing but it is going to be divided into blocks. Okay. Suppose your plain text is going to be of 300 bits. Okay. So here the algorithm which we are going to be used based how that blocks are going to be divided. Block size is going to be divided based on what kind of algorithm you are going to be using. Suppose plain text is equal to 300 bits, right? So here, can you see my mouse pointer?
Yes, ma'am, we can see it.
Yeah, okay, thank you. So plain text is equal to 300 bits, right? So here what is going to the algorithm we are going to be using? AES 128 algorithm we are going to be using. Okay. So then what is the key size? It is going to be 128. Okay. So whatever this 300 bits is going to be there, that is also divided into each block of size 128 bits, because the algorithm which we are going to be using is AES 128. Okay, so block 1 is equal to 128, block 2 is equal to 120, another 128 bits. So block 1 is going to be 1 to 128 bits, block 2 is equal to 129 to 256 bits, and block 3 is equal to 257 to 300 bits. So like that you are going to be having, and also once you are going to be having, so if you observe, block 3 has got only 44 bits, the other remaining bits are empty. What you need to do then, so until you get 128 you are going to be filling with zeros. Okay, so that's how you are going to be obtaining the values. And also if the algorithm is going to be of DES, so DES key size is equal to 64. Okay, so then this 300 is going to be divided into 64, 64, 64. Whatever the final bits are going to be left over, that is going to be filled with remaining zeros, and it is equated to your 64. Okay, so that's how your DS is also going to be working. So finally, whatever the blocks are going to be got, so those blocks of your plain text are going to be encrypted, and they are going to be converted into the ciphertext individually. Each block is getting converted individually. Okay, so that's how the electronic codebook is going to be working and all. So let us see the electronic code book ECB encryption and the decryption process. Okay, so here as one. Okay, so electronic code book and all. So any time, so whatever the plain text is going to be got, that is going to be divided into blocks. Okay, so first block, that is going to be a P1. First block plain text is P1. Second block plain text is P2. So on up to Pn is going to be the nth block plain text. Okay, so whatever this plain text is going to be there, that is going to be encrypted, and that is going to be got into the cipher text. Okay, so like this plain text is encrypted up to cipher text. Okay, so plain text is encrypted and you are going to be getting cipher text. Okay, so this is going to be regarding your block number 1, and this is going to be regarding your block number 2, until like that you are going to have the last block, that is going to be a nth block. So that is going to be a plain text nth block encrypted, converted into the ciphertext. Okay, so like this each block is going to be encrypted and you are going to be getting the ciphertext. Okay, so if at all we are going to be getting one block ciphertext, you are going to be getting, or few blocks of ciphertext. So C to all the odd even numbers you are going to be getting. Okay, so C2, C4, C6, C8, like that, C10, some few blocks of ciphertext you are going to be getting. So that ciphertext is going to be taken and it is going to be decrypted, and the same what is the P2 is going to be obtained after decrypting it. So that is going to be a plain text of your block number 2 is going to be gotten. So here whatever initial here what is the problem here, the blocks and are going to be encrypted and can be decrypted individually. So here reversible mapping is going to be possible, and here what is going to be, it's going to be ECB is going to be more prone for attacks, because once they get the ciphertext, the few ciphertext also they are able to convert into the plain text, and they are able to guess what is the other plain text can be. Okay, so like this they might break that encryption process. So that is going to be a electronic codebook. Okay, so the Decryption is going to be nothing but the ciphertext C1, C2. So this is going to be the first block ciphertext. C2 is going to be the second block ciphertext. Cn is going to be the nth block ciphertext. Okay. So that is going to be given for your decryption algorithm along with your key, and you are going to be generating the plain text of your first block from your C1. Plain text of your second block with your ciphertext 2. Okay. So like that you are going to be obtaining the whatever the process is going to be there, okay, for your decryption and your encryption. Okay. So this electronic code book is going to be having few pros and cons. You are going to be having advantages and your disadvantages we are going to be having. First one is going to be, it is going to be the simplest mode operation which is going to be done. So simply from your conversion of your dividing the plain text into the blocks, and each block of your plain text is going to be converted into the ciphertext and all. Okay. So this ECB is going to be no, it's going to be very ideal for your short amount of data, and also whenever you want to do a secure transformation of your AES or your DES, you are going to be doing and all. So next you are going to be having an independent of your encrypt. You can encrypt any block and all. So this is going to be each block is going to be encrypted individually, and each block can be decrypted individually. Okay. So that is one more advantage you are going to be getting here. And it is going to be fast because it's going to, they are going to be working parallelly. Once you are going to be dividing whatever the plain text you are going to be getting into, suppose 10 blocks you are going to be doing. At the same time, these 10 blocks are going to be working parallelly in order to get the ciphertext. So that's going to be parallelly. Whatever, if we say like first block conversion into the ciphertext, then only the second block plain text can be converted into the cipher text of your second block. After completion of your second block, only third block will be converted, fourth block. So then what will happen? Lot of waiting time. Suppose for 10 blocks, each block is going to be taking 10 minutes. So 10, 10, 10, like that, it is going to be having almost 100 minutes, more than 100 minutes. Okay. So if it is going to be, they are going to be working individually. So all these 10 blocks of your plain text is going to be converted into the ciphertext. So within 10 minutes of time, 10 blocks are going to be converted into the ciphertext. Otherwise, if they are not working parallelly, so then what will happen? Each one needs to compute one all. Okay. So here, this ECP is also going to be having certain disadvantages and all. So what are those? It's going to be not secure for your lengthy messages and all. So because whatever the crypt now, already I said that we easily, whatever the few ciphertext you are going to be knowing, so easily you can reconvert them into the plain text, do the reversible mapping, and your system is going to be prone for attack and all. So these whatever the script analyst is going to be there, so they are going to be whatever this regularities of the message are going to be there, or the pattern of that particular conversion of your plain text to the ciphertext and all. So if the crypt analyst or the attacker or the opponent are going to be getting that spoof of information and all, so easily they can exploit whatever the regularities are going to be available as part of these kind of encryption and decryption process. So in your ECB mode. Okay, so this is going to be the well-known example for you. So this is going to be the well-known example for your ECB. So the original message of your ECB is going to be a penguin penguin image. Okay, so ECB also is going to be working for the images, right? So pick 2 is going to be nothing but whatever the encryption is going to be done. So that is going to be done with respect to your ECB, after which the figure is going to be looking like this. So this is going to be the decrypted format of your ECB original message. Okay. So now as part of your ECB here, if you observe, you are able to see this particular outline, right? So if the cryptanalyst or the attacker is going to be seeing this outline and also, they they will be able to get the information. Okay, by seeing this outline, we are able to recognize that this is going to be something similar to a penguin and all. Okay, so that is going to be nothing but the information is going to be gotten, which is not going to be matching with respect to whatever the security that algorithm should be providing and all. So as part of if we are going to be using an is I mean to say that if we are going to be encrypting the original message by using the ECB, so then it is going to be showing whatever this outline is going to be shown. So this pattern is going to be shown. So by which you are able to guess that it might be a penguin and all. Okay. So but once this penguin image is going to be encrypted with other modes of operation, we are going to be having like this blank kind of thing. So no, we are not able to make any guesses here. So being an attacker or a cryptanalyst. Okay. So here your the attacker and the cryptanalyst will be able to succeed in guessing the original message and they can get hold of the data. So this is going to be what ECB is going to be. Any doubts? Okay, proceeding to the second one. So that is going to be a cipher blockchaining. Okay. This is going to be somewhat similar to your blockchain working and all. So how that is going to be working, I will let you know now. Okay, so cipher blockchaining. So this whatever that ECB is going to be there. So what you are going to be getting, whatever the same plain text of your block number one is converted into the cipher text block number one. Okay, so for which as part of your same P1 is mapped to your C1. Okay, so P2 is mapped to your C2, like that. Whatever the same plain text block is going to be there, that is going to be the same ciphertext block are going to be matched. Okay, so this is going to be similar, like you are going to be matching the same dress top and bottom, you are going to be matching. Okay, CBC is going to be somewhat different. Okay, so no, so top is going to be different for the plain text and it is going to be a different bottom you are going to be working. So this is going to be a difficult one in order to crack whatever the cipher plain text is going to be there. How it is going to be, we will see now. Okay, so here the cipher block chaining also is going to be using the same key as part of your entire algorithm and all chaining and all. So here what is going to happen and all, so whatever the repeated bits of your patterns are going to be there, they are not going to be exposed and all. Okay. So okay. So this is how your cipher block chaining is going to be working with respect to the encryption and decryption we will be seeing. Okay, cipher block chaining. First, let us see the encryption. Okay, if you check here, you are going to be having the so just discard the decryption diagram. Just concentrate on your first block of your encryption. Okay, so this whatever the mouse pointer is rotating at. Okay, so here first you are going to be, what is the first block plain text? It's going to be represented with P1, right? So then you are going to have IV. What is this IV? This is going to be represented as initial vector, and this is going to be considered as an initial input for your encryption and your decryption. Both procedures here IV is going to be important. Okay, so this is going to be considered as an initial vector. Okay, so whatever the plain text is going to be there and this initial vector is going to be there, that you are going to be doing an XOR operation, and after whatever the output is going to be got, that is going to be given to the encryption algorithm, and that encryption algorithm is encrypting that particular result and it is going to be generating the ciphertext. So whatever the plain text is coming, is it the same plain text you are encrypting and getting the ciphertext? So no. Hello? Girls, I asked you a question. Here? No. Answer is going to be no. So whatever the plain text is going to be there, so we are going to be converting into the encryption format, whatever the XOR operation, and then the result is going to be again encrypted. We are not passing the same plain text for your encryption like your EBCE. Okay, like your electronic code book ECB. Okay, so in cipher blockchaining, we are going to be using something called as initial vector and the plain text, and you are going to be doing an XOR operation, and you are going to be encrypting, and you are going to be getting the cipher text. Okay, so like this here, whatever this cipher text is going, why I said that it is going to be similar to your blockchain and all. So whatever this cipher text is going to, previous block hash value is going to be mapped to the next block hash value. So like that only in your blockchain. So like that only whatever the cipher text of your first block is going to be there, that is going to be given to your plain text of your second block, and that is going to be XOR, and you are going to be giving that result to the encryption algorithm, and the encryption algorithm is going to be getting your cipher text for your second block. Again, this cipher text of your second block is going to be given as input to your third block. Okay, so like that here, Cn minus 1 is going to be given as your input for your nth block. So Pn for Pn and Cn minus 1 both are going to be XORed, and whatever the result we are going to be yielding, that is going to be given for your encryption algorithm, and finally you are going to be getting the cipher text of your nth block. So that's how your encryption algorithm is going to be working. Any doubts, please ask me. Any doubts? Are you listening? Is there anyone in the meeting?
Yes, ma'am.
Did you understand now? You want me to repeat? Monday namma exam. Did you understand, yes or no? అర్థమైందా అర్థం కాలేదా? Okay, no waste of time. This is all. Okay, so here next is going to be a decryption process. So decryption is also going to be done in the similar manner, but whatever the ciphertext is going to be done, so first that is going to be decrypted, then you are going to be whatever the result is going to be got, then you are going to be making an XOR operation with the initial vector, and you are going to be getting the plain text. Okay, so this is going to be reverse manner. So whatever the ciphertext is going to be there previously, so that is going to be given as input for your next block of your decryption. So like that you are going to be giving the ciphertext 2 to the block operation of your 3. Okay, ciphertext 3 to the block operation of your 4. Okay, so ciphertext n minus 1 to the block operation of n. Okay, so like that you are going to be doing the decryption algorithm. Okay, so these are going to be the pros and cons of your cipher blockchaining and all. So here what is going to be done, whatever the messages, encryption of your messages and all, as the initial vector is going to be involved and all. So whatever the encrypted message is going to be, this is going to be little bit greater than whatever the size of your actual plain original message is going to be there. Okay, so here you are going to be following these two properties properties. So those are going to be a confidentiality and your authentication you are going to be following. So as part of your security trade, you are going to have the CIA. So here confidentiality and authentication are going to be following. Okay, as part of your CIA, whatever that confidentiality, integrity, and availability are going to be there. Not only those three, along with that, you are going to also you need to satisfy two more properties. So those are going to be the authentication and the authorization. So all combined together, you are going to be getting the security trade satisfied. Okay, so here cons are going to be, disadvantage is going to be, unless until your first output is going to be generated and all. So first block output ciphertext is going to be got, and because that output is going to be used as an input for the second block, so it cannot be done parallel like in your ECB. Okay, so in your ECB it can be done in parallel, whereas your CBC it cannot be done in parallel. Okay, so you need to encrypt. So you cannot encrypt any block of your ciphertext of your previous block and all. So because you will be requiring the entire links of your ciphertext. So that then only you will be able to decrypt and all. So initialization vector. So this is should be known to your sender side and the receiver side, because sender is going to be doing their encryption process, initialization vector is going to be used, whereas your receiver is going to be doing a decryption process, for which also initialization vector is going to be required. Okay, so this is going to be the differences. So this is going to be many times repeated question. So comparison with respect to your ECB and your CBC. So sometimes, mostly I am expecting it to be short answer question. So sometimes they are going to be asking a long answer question also. So better we have prepare for your long answers. So okay, so this is going to be the definition. So it's going to be a single block value, and it's going to be encrypting whatever the multiple values are going to be there. So here small messages, this is going to be for larger messages. This is going to be easy to decode, and also this is going to be difficult to decode. ECB is going to be whatever the block of your plain text is going to be there. So that is going to be converted into ciphertext, corresponding ciphertext block, whereas your CBC is going to be there. So that block of your plain text is going to be whatever the original message is going to be there. So that is going to be generated with respect to your ciphertext along with your initialization vector and your XOR operation. Okay, so here as part of your ECB, they are going to be using a feedback mechanism, whereas your CBC, sorry, ECB is not going to make use of feedback mechanism, whereas your CBC is going to be making use of your feedback mechanism. That feedback is not required actually. That point can be eliminated. So ECB is not going to be using initialization vector, whereas your CBC is going to be using the initialization vector. What is that initialization vector, how it is going to be used as part of your encryption and decryption process, that's already discussed with you. Okay, so ECB, so are they doing any XOR operation for gaining the ciphertext from your plain text? No. So whereas your CPC, they are going to be using the, they are performing the XOR operation, they are going to be getting the block. So here, if you observe, I did not discuss this point. Why? Because this is the point, main point I have been stressing, and also that is nothing but as part of your ECB and all. So it's going to be nothing but reversible mapping is possible, I said. So whatever the plain text is going to be, that is going to be divided into first block, second block, third block, up to nth block, you are going to be divided. Whatever this plain text is there, so that is going to be given as an input for your encryption algorithm along with your key, and you are going to be getting the ciphertext. So similarly, once you get this ciphertext, you are able to reconvert it into the plain text in your ECB. So that's why it is going to be is not secure algorithm, whereas your CBC already have explained that whatever that plain text is going to be there, along with your initialization vector, you are going to be doing XOR operation, and that is going to be given as an input for your encryption algorithm, and then it is going to be generating a ciphertext for the first block. And this, whatever the ciphertext is going to be got, that is going to be used in the place of initialization vector from the second block. Okay, so second block, what will happen? Plain text 2 of your second block. So plain text 2 is going to be represented as second block plain text. Okay, so next C1 is going to be coming as another input. Both for both XOR operation is done, then the encryption, and then you are going to be getting the final output of your C2 you are going to be getting. That is the ciphertext of your block 2. Okay. Again, this ciphertext of your block 2 is going to become an input for your block number 3. Okay, block number 3, plain text, block number 2, ciphertext, both XOR together, and encryption algorithm, you are going to be giving the input, and finally you are going to be getting the ciphertext of your third block. Okay, so that's how it is going to be performed. So the last mode of operation as per your syllabus is going to be a cipher feedback. After this, I will leave your class, and evening I will take a class from 7 to some 8:30, or 1 hour is going to be done based on your understanding, girls. Okay. So the last one is going to be a cipher feedback. Okay. So before that, what you will see is RSA algorithm, how it is going to be working, and Diffie-Hellman key exchange, how they are going to be working. Those two topics are going to be left. Triple DS is going to be just taking some 5 minutes, 10 minutes of time. So RSA and Diffie key Hellman key exchange are going to be very important. Okay, so those needs to be discussed with along with the example. Okay, so that will be done in the evening class. Okay, so for the last mode of operation is going to be the cipher feedback operation. Okay, so as part of your cipher feedback operation, and also whatever the block cipher we are going to be getting, we are first converting into the stream cipher. Okay, so once it is going to be converted into the stream cipher, and also you don't require any padding. If you remember in the block cipher, once you are dividing into the blocks, and after dividing into the blocks, if it's going to be shortage of bits for that block length and all, you are filling with zeros and all. So those kind of padding techniques is not going to be required in your stream cipher. Why it is not required? Once you are going to be getting a data, that is going to be converted into the binary format, that is going to be sufficient for whatever the size is going to be there. So as part of your stream cipher, so we don't require any padding and all for that reason. Okay, so next is going to be the real time. So what is this real time scenario and all? So once you are going to be getting the bits and all, dynamically you are converting into the ciphertext, and you can just keep on sending the data, whatever the batch you are going to be getting. Okay, send. So you need not wait until all the bits are converted into the ciphertext and then only send all the bits at a once and all. That is not required in your stream cipher. Okay. So they are going to be working on the authentication technique, and they are going to be working on the stream oriented transformation. So this is how your stream. So this is little bit tricky, girls. I don't say anything difficult. So I will say tricky. Okay, so because it, if you understand the thing, it is going to be simple. If you don't follow or don't concentrate, then it is going to be difficult for you. Okay, cipher feedback mode, what is going to be there in your cipher feedback mode? Also, this is going to be for encryption. Okay, so here also you are going to be having for your initial vector is going to be there. Okay, so this initialization vector is going to be given as an input, and key is given as an input for the encryption algorithm, and here going to be giving a output. Okay, as part of this output, you are going to be selecting your S bits, and that S bits are going to be forwarded. Please listen, girls. Only as part of your whatever the ciphertext output is going to be got from your encryption, only S bits are going to be selected, and that is going to be XORed with the plain text one. So plain text is going to be not coming initially. After you get the output of your encryption, how you are going to be getting initialization vector, and the K you are going to be having the encryption, and you are going to be getting some output, and that output is going to be converted into the S bits, and that plain text along with the S bits are going to be XORed, and that is going to be given as ciphertext of your S bits. Okay, this is now used as an input for your next block. Okay, so next block also what you are going to be doing, whatever this register is going to be there, so this is going to be C1 is going to be for S bits, right? So you require the B minus S bits are going to be missing and all. So that B minus F shifts, how you are going to be getting, you are doing a left shift operation here. Okay, so how whatever the S bits are going to be there, so for that S bits whatever the plain text is going to be there, for that you are making a left shift, and you are going to be discarding the first element, because your how the left shift is going to be there. I'll show you one diagram. Okay, do you observe this one? Yeah, sure. Okay, so this is going to be the thing done. What it is going to be doing, whatever element is there, it is making shifting one place, one place, one place. Whatever the last element is there, so first element is there, that is going to be dropped off. And if you observe, so 0, 1, 0, 0, 1, 1. So that's what we have got here. Okay, so 0, 1, 0, 0 we have got here, and now last bit is going to be, you don't have any bit, so this last bit is going to be replaced with 0. So that 0 is going to be replaced here. Okay, so that's how your encryption is going to be done. Okay, so this is how your shift operation is going to be done, and you are going to shift operation is going to be done, and you are going to be getting the B minus S bits from here. S bits is going to be got from your C1. B minus S bits is going to be S bit only kada ikkada drop off చేసేస్తున్నాం. అలాగా you are going to be having B minus S bits here. So both are going to be taken and you are going to be doing a OR operation and you are going to be doing the encryption along with your key. And again what you are doing, B minus S bits you are discarding, again you are selecting the S bits and you are going to be doing the XOR operation. So this is going to be the final P2. Okay, again what is going to happen, so here whatever the C1 is going to be there, this C1 is going to be given as input for the next block. Okay, similarly, for your nth block, C n minus 1 is going to be given as input, and the other input is going to be a K and left shift, and you are going to be this. So this is going to be C n minus 1 is going to be S bits, and left shift is going to be your B minus S bits. So entire thing you are going to be encrypting, and whatever the result you are going to be getting. So for that, your S bits are going to be selected, and you are doing a XOR operation, and you are going to be getting the plain text where you are going to be discarding certain bits. Okay, so this is what is going to be a CFB decryption. So this is what by this your third part, until your third part is completed, except one topic, that is the triple DES. So that will take only 5-10 minutes, I can see. So that evening class will meet. I need to go. Okay. So next RSA algorithm and Diffie-Hellman I will explain. So these two topics, LGML I'm not going to discuss for your mid. So the syllabus is going to be up to your 2 units except the last topic of your that is LGML. Okay. Yours is GNR 18. Ma. So everything we are going to be covering. So until Diffie-Hellman key exchange, you are going to be having all these series. Okay. Thank you, girls. You can leave 1 second. I'll take the attendance. You can leave, ma. Thank you very much for joining. Mm, sorry. Okay. Thank you, guys.